Hello, my dear friends. Welcome to the Sharpage update. I Deepak here, and today I am explaining how we can find the value of electrical potential at a point inside an electric field. And first of all, we have to know what is the meaning of potential. So let's start now. Now, at first, I am telling about the meaning of potential. So dear friends, potential means electrical potential at a point inside an electric field is defined as the ratio of work done in bringing a test charge from infinity to a point inside an electric field to the magnitude of that charge is known as the electrical potential. It means if Q charge is brought from the infinity to a point inside an electric field and the total amount of work done in bringing a test charge at that point is represented by W, then we can write electrical potential V equal to W upon Q. Here we are finding electrical potential. So electrical potential V is represented by W upon Q. If we take Q equal to plus 1 coulomb, then we can write here V equal to W. It means, in other words, we can say that the electrical potential at a point inside an electric field is equal to the numerical value of the work done in bringing a unit positive charge from infinity to that point. Here, I am taking Q equal to plus 1 coulomb. So, this charge is known as the unit positive test charge, and unit positive test charge is represented by Q0. As I told you before, means in previous video I have explained the meaning of unit positive test charge. Now, the SI unit of electrical potential is volt. And other SI units of electrical potential can be written as, here you can see that V equal to W upon Q. The SI unit of work is joule and the SI unit of charge is coulomb. So, another SI unit of potential can be written as joule per coulomb. And another unit of electrical potential in SI system is, suppose W equal to force into displacement and divided by charge Q. And the formula for force with the help of second Newton's law of motion, we can write here F equal to mass into acceleration into distance divided by charge. And the formula for charge equal to, as we know that electrical current I equal to the rate of flow of charge. It means electrical current is represented by Q upon T, where Q represents charge and T represents time. So the value of Q can be written as I into T. And the SI unit of electrical current I is ampere and the SI unit of time is second. So it can be written as ampere into second. Here mass and acceleration. Mass into acceleration means meter per second, and the SI unit of mass is kilogram. SI unit of acceleration is meter per second square. SI unit of displacement is meter upon ampere into second. So, another unit of electrical potential can be written as kilogram meter per square per second cube. सेकेंड पावर माइनस 2 एंड सेकेंड ये मिलकर हो जाएंगे सेकेंड पावर माइनस 3. सो किलोग्राम मीटर स्क्वायर सेकेंड पावर माइनस 3 इंटू एम्पियर पावर माइनस 1. सो इलेक्ट्रिकल पोटेंशियल की ऐसा यूनिट्स को हम वोल्ट, जूल पर कूलम एंड किलोग्राम मीटर स्क्वायर पर सेकेंड क्यूब पर एम्पियर लिख सकते हैं. एंड द सीजीएस यूनिट ऑफ इलेक्ट्रिकल पोटेंशियल इज स्टेट वोल्ट. And the electromagnetic unit of electric potential is amp volt. Now, the relation between SI unit of electric potential and CGS unit of electric potential and electromagnetic unit of electric potential as volt equal to 1 upon 300 stat volt equal to 10 to the power 8 amp volt. So this is the relation between CGS unit and SI unit and electromagnetic unit of electric potential. Now, another thing, if we want to find the dimensional formula of electric potential with the help of this unit, we can find the dimensional formula of electric potential. As you know that kilogram means mass, so m, meter means length, so here L square, second means time, means 3 to the power minus 3, and A shows ampere, A to the power minus 1. It means the dimensional formula of electrical potential is m L2t minus 3 A power minus 1. Now, I am finding the expression for electric potential at a point inside an electric field. So, for finding the expression for electric potential at a point inside an electric field, let a point charge plus Q is placed at point O, and the electric field due to this positive charge will be the area surrounding of this charge. Means let the electric field due to this charge is this. Means area surrounding this charge is known as the electric field. Now at point P we have to find the electric potential. And friends, as I have told you, the electric potential is the amount of work done in bringing a unit positive charge from infinity to a point inside an electric field. Here I am using the word from infinity or from infinite. It means when the charge is kept out of this area, means out of the electric field, then the charge is assumed as kept at infinity. Means यदि चार्ज इस इलेक्ट्रिक फील्ड के बाहर रखा हुआ है तो हम कहते हैं कि वो चार्ज इंफिनिटी पर है. Means we are bringing the unit positive test charge from the outside of this electric field. It means from the infinity at this point inside an electric field. So from infinity we are bringing a unit positive test charge Q0 at this point. And let we are shifting from a small distances. Means first of all the unit positive charge is kept at point A, then at point B, and finally we kept this unit positive test charge at point P. Means we are bringing the unit positive test charge from infinity to point A, then point B, and then finally at point P. And let this is means AB distance is represented by TS, means very small distance, and the distance between point O and point P is represented by R, and the distance between point O and point A is represented by X. So here you can see this distance is represented by dx, distance OP is represented by R and distance OA is represented by S. Now, we are moving a unit positive test charge from infinity to a point A, then to point B, and then at the very small distances, we are moving the unit positive test charge to the point P. So, the force means electrostatic force due to discharge on the unit positive test charge Q0 will be represented by F equal to 1 upon 4 pi epsilon 0 into Q0 upon X square, when the unit positive test charge is at point A. And as we know that by the Coulomb's inverse square law, electrostatic force equal to 1 upon 4 pi epsilon 0 into Q1 Q2 upon distance square, and we assume that the charge is kept inside the medium of air or vacuum. Now here Q1 is discharge and Q2 is the unity positive test charge. Now, as we know that the electric potential is the total amount of work done in bringing a unit positive test charge from infinity to that point. So, the work done means when we are shifting the unit positive test charge from point A to point B means by very small distance. So, the amount of small work done dW in shifting a unit positive test charge from point A to point B means by very small distance. So, work done equal to force into displacement. It means dW equal to force into displacement here dx. So, here I am using dot product means force dot dx means scalar product, or you can say that dot product. And as we know that the scalar product means A dot B means scalar product of two vectors can be written as modulus of vector A, modulus of vector B into cos theta, where theta is the angle between these two vectors. In this case, we can say that force F means force between plus Q charge and the unit positive test charge will be repulsive force because both are positive charges. So, the direction of force will be in this way, and the displacement direction means the direction of this displacement. We are moving the unit positive test charge from point A to point B. Hence, the direction of displacement will be in this way. So here, dW equal to F dx cos theta, where theta is the angle between the direction of force and the direction of displacement. And we can see by this figure, the angle between the direction of force and the displacement is of 180 degree. So we can substitute 180 degree here in place of theta, means dW equal to F dx cos 180 degree. And as we know that the value of cos 180 degree is equal to minus 1. So we get dW equal to minus F dx. By substituting here minus 1, we get dW equal to minus F dx. So, for calculating the total amount of work done in bringing a unit positive charge from infinity to the point P, we have to integrate this relation. It means dW equal to integration of F dx, and the limits will be when the charge is at infinity, means when the charge is at infinity, then there is no amount of work done. And when the charge is at point P, means from the distance charge Q is R, then the amount of work done is taken as W. So by substituting the value of F here and by taking the limits of this integration and by using the formula, we get W minus 0. And as we know that integral of dx equal to x, so integration of w is equal to w, and by substituting the limits, first limit means upper limit minus lower limit, so we get w minus 0. equal to minus integration infinite to r 1 upon 4 pi epsilon 0 q0 upon x square dx. Means by substituting the value of f from here f equal to 1 upon 4 pi epsilon 0 q0 upon x square. Now this will be w equal to minus, and we know that the constant values comes out from the integration, then 1 upon 4 pi epsilon 0 q0 and 1 upon x square. So 1 upon x square can be written as x to the power minus 2. So x to the power minus 2 dx, and the limits are infinite to r. Now friends, as we know that the formula for x to the power n dx equal to x to the power n plus 1 upon n plus 1, where n should not be equal to minus 1. Here you can see that n is equal to minus 2. So we can use this relation for finding the integration of this. So w equal to minus 1 upon 4 pi epsilon 0 q0 x to the power minus 2 plus 1 upon minus 2 plus 1. So here I am writing directly. By solving this integral with the help of this formula, we get minus 1 upon x, and the limits are this, infinity to r. Minus and minus makes positive sign, so we get w equal to 1 upon 4 pi epsilon 0 q0, and by substituting the limits means upper limit minus lower limit, so we get 1 upon r minus 1 upon infinity. This minus sign and this minus sign makes positive, so ये दोनों साइन यहाँ से हट जाएंगे, and by substituting the limits we get 1 upon r minus 1 upon infinity. And as we know that the value of 1 upon infinity is always equal to 0, so this term will be 0. 1 upon r minus 0 equal to 1 upon r, so we get w equal to 1 upon 4 pi epsilon 0 into q0 upon r. And as we know that the electric potential is equal to the amount of work done in bringing a unit positive test charge, means q0, from infinity to a point inside an electric field. So we can write here electric potential V equal to W upon Q0. Here Q0 represents the unit positive test charge. So by substituting the value of W from here, we get V equal to and then upon q0 into 1 upon q0. 1 upon 4 pi epsilon 0 q0 upon r is the value of work done, means value of w, and into 1 upon q0, so this 1 upon q0. Now by cancelling q0 with this q0, finally we get the expression for the electric potential as V equal to 1 upon 4 pi epsilon 0 into Q upon R into Q upon R volt. So this is the expression for electric potential in SI system when the source charge, this charge plus Q, is kept inside the medium of air or vacuum, and all the measurements are taken in SI system. Expression will be V equal to 1 upon 4 pi epsilon 0 into Q upon R volt. So my dear friends, in next video I will explain the Kirchhoff's law, means Kirchhoff's current law and Kirchhoff's voltage law, for finding the value of equivalent resistances or the value of current in an closed circuit. Till then, goodbye. Please like and subscribe the channel, the Sharpage Update.